I wanted to be something a little different, showing that we've progressed a little further. And here's some of the stuff that we have actually been building up upon in the time since, and we've got some really cool data to show you. So as you can see, we're talking about segmental mass properties, hence why this Triceratops is all those different colors. We've divided it into segments. But I'll give a little about me to those who don't already know. I'm currently a PhD candidate at Oklahoma State, studying under my advisor, Dr. Eric Snively. I'm mainly focused in paleoecology, so understanding what the ecosystem was like, what the organisms in it were doing, and how they interacted with each other. And I'm focused on a particular time period, the very end of the Cretaceous, between 68 and about 66.25 million years ago. I also have a lot of background in working with modern reptiles, i.e. neontology, both for research and as a passion/hobby. And I've gained an appreciation especially for their behavior and complexity, which is something that's often overlooked in paleontological studies of like even dinosaurs, where they'll talk about them being primitive or having simple behavior because they have a reptilian brain organization. That's all a bunch of bunk. But dinosaurs. So here are a couple cornerstones of my work. Obviously, field work. You know, we need to get fossils and other material out from the field to figure out what's going on. Here's an example of me out in North Dakota working, bringing out a jacket from Tyrannosaurus Rex dig site. And that's, like I said, that's how we learned what was there, what the climate and the environment were like, both through geology and through things like paleobotany and all sorts of other things. But another thing is extant field work. We need what's called ground truthing, because you can make all these hypotheses about these extinct organisms, but if you don't have any reference to living things where we can actually observe interactions, then you're kind of just, you know, throwing things into the wind. So here's an example, me in South Africa, showing the effectiveness of camouflage. You might not see an animal there, but now you do. Puff adder, neonate, less than a week old. And here's just an example of an insight that I had after going to South Africa that people might not think of just when they look at the fossil record in a vacuum. And specifically, we're talking about turtles and megafauna. And this was an observation that I made in April of this year. So the big animal, you can't really see what it is. That's a white rhino. Those are ticks. And that is a hungry turtle eating ticks off of a wallowing rhino. Here's a hypothesis about paleoecology that we can derive from that. Here you've got a Triceratops, the equivalent in terms of being megafauna, megafaunal herbivore. We know, based on the fact that it occurs often in floodplain-based mudstones and stuff like that, that it was probably living in kind of swampy, flooded areas. We know that ticks were present because we found them in amber dating to about 99 million years ago. And ticks are pretty ubiquitous. If there's large animals, there are ticks. We know there were turtles around. So it's reasonable to hypothesize that these turtles may have done the exact same thing. It's a resource, something's exploiting it. So that's kind of something that we can learn that you wouldn't necessarily think of just looking at turtles or dinosaurs in the fossil record. But when you have this extant ground truthing system to look at them in, it shows things in a new light. Then cornerstone 3 for my work is biomechanics. This relates to forces acting on an organism, including muscles and bone, which are the main things we're looking at because we're looking at fossils. We don't have things like, you know, circulatory system. We don't get fossil arteries or, you know, aortas or pulmonary systems. And we can use this to infer function and potentially even behavior in these extinct animals. One of the most popular examples is estimating bite force, where you look at the sizes of muscle attachments and where they're located, and you compare them to modern animals to get kind of ideas for the soft tissue characters you can't directly get from the fossil record, and you reconstruct that and figure out what was going on there. My focus specifically is on what we call locomotor performance. In other words, that's kind of fancy talk for how the animal moves and how good it is at doing that. That diagram there is a very nice diagram showing the various forces, both muscular and ground reaction, at work during the stride of a Tyrannosaurus Rex, courtesy of my student Adrian Bowie. But locomotor performance isn't just one thing. It has many components, and those need to be integrated together to understand it. It's kind of like if any of you guys ever remember Captain Planet, you've got top speed, agility, turning ability, linear acceleration, how fast can that animal get to its top speed? Stance, is it parasagittal, is it sprawling, etc. Locomotor mode, is it scansorial, is it arboreal, is it saltatorial, hopping? And when you have all of these together, that is locomotor performance. But now we're going to segue into what mass properties have to do with that. They help us understand movements. They give us properties like the center of mass and the inertial properties of these bodies. And when we put these together, we can use them to infer function. I will give you guys one of the early examples that we did, which is mass properties in the head of Tyrannosaurus Rex. So you can have mass properties that resist movement, so things like rotational inertia, also known as mass moment of inertia, and center of mass. You can see here kind of how that can resist motion. And center of mass also deals with rotation about different axes. So here what we did, we took this digital reconstruction of the skull of a T-Rex specimen named Victoria. We took the volume of the bone and we used the density of modern bone to figure out that segment of the mass properties. Then we reconstructed the brain based on the hollow area inside the brain case. And we gave that its own density. And then we gave the airspaces kind of a zero density. Then we did the soft tissues, sculpting those around based on muscle reconstruction and the kind of phylogenetic bracket, as well as the inference that these animals did actually have non-muscular lips, also called the lizard-informed version, kind of colloquially. And then what we can do is we basically, so we get each of those components, the volume contributed to the total head of each of them, we multiply them by their respective densities to get the mass properties of the entire object, in this case, the head, as a whole. So in this case, the skull itself weighed about anywhere from 112 to 171 kilograms. The head as a whole was about 617 kilograms. And the rotational inertia for lateral motion, so flexing side to side around the occipital condyle where the head connects to the neck, about 94.8 kilograms times meter squared. With rotational inertia, basically the higher it is, the harder that thing is to move in a given direction. So that's surprisingly low. And then we can look at the muscles in the neck that are responsible for moving the neck side to side. Two of these, the complexus muscle and longissimus capitis superficialis. So the complexus muscle swells in baby birds to assist with hatching. And then for longissimus capitis, in T-Rex, the tendons for that muscle are as big as bridge cables. So look at the Golden Gate Bridge, look at those cables, that's how thick those tendons were. Now, we can look at what that would look like for turning. Here we have in kind of a oblique and then a top view. That's it turning its head. And then from the top, that might not seem all that fast, but keep in mind that was in slow motion. Let's see without slow motion. Much faster, like ludicrously fast. T-Rex could turn its head insanely quickly. If a racehorse was running at full speed in front of a T-Rex, the T-Rex would easily grab it. But this is only the head. We need more context if we really want to understand the animal. And so that's where we're kind of expanding. We have to consider the ecosystem. And T-Rex lived alongside many other dinosaurs, including frilled ceratopsians like Triceratops, the duck-bill hadrosaurs like Edmontosaurus, ostrich-like ornithomimids like Struthiomimus, the hell chickens, as I like to call them, the Caenorgnathids, like Anzu and the smaller Eoneophron, the dome-headed pachycephalosaurs like Pachycephalosaurus, and more. And so what we have to do now for that additional context is more species and more parts of the body. So we take the whole bodies of multiple taxa, we split them up into multiple functional segments, and we can use those properties to get performance estimates with simulation software, though that simulation is still currently ongoing. We can still get some preliminary ideas just from what we have right now. So let's slice a couple of them up, right? Here's a Tyrannosaurus Rex. You can see, it's hard to see here, but the head, neck, torso, and tail are all their own distinct segments. It's, again, hard to see because of the size of the arms, but the arm is divided into 3 segments, the stylopodium, the humerus, then the forearm or zygapodium, and then the metapodium, the hand itself. And then the leg, you've got your thigh, calf, ankle, and then each toe is actually divided into multiple segments because we now know that the foot was incredibly important in how these animals move, which has been historically underestimated. Then here we have Triceratops, same thing, though you can't see it here because the scale and because its fingers were very tiny, but here we actually have, like with T-Rex and its toes, we have segmented out the fingers because it was a quadruped. We didn't do that for Tyrannosaurus Rex because it's not using its fingers to move. We've done the same thing with Edmontosaurus and Anzu. And let's first off look at just a preliminary comparison. We can look at how much soft tissue mass is dedicated to locomotor muscles. For the bipeds, we used the hind limbs, the tail, and then gave about 10% of the torso mass for some of those adductor muscles and the like that would extend into that segment as seen before. And then for the quadrupeds, all of the limbs, as well as the tail and about 10% of the torso. So let's see how they measured up. Tyrannosaurus Rex, a nice 40%. Edmontosaurus, 41%. Anzu, 44%. Triceratops, 26%. Pretty interesting. So Tyrannosaurus, Edmontosaurus, and Anzu all have comparable locomotor muscle mass proportions. So Edmontosaurus and then especially Anzu could have a good chance at outrunning a Tyrannosaurus Rex. Partially for Anzu, it would be a piece of cake because the Tyrannosaurus Rex at its large size is limited by mass. But Triceratops has far less locomotor muscle mass, which suggests a very different predator avoidance or deterrence tactic compared to something like Edmontosaurus. So that alone, we can't use just those numbers to really infer because there are potentially many different explanations for it. But let's look into why. Here we've got our Triceratops. You can see that the limbs are very short. It would not have a very long stride. And as you can predict, the stride length multiplied by stride frequency gives you speed. And the shorter the length, if you keep frequency the same, the slower that animal is going to be. Also, it had a small tail, which means there was less caudofemoral muscle. Caudofemoralis is the major muscle in most dinosaurs, especially kind of less bird-like dinosaurs that pulled the thigh backwards and contributed to acceleration and general motion. So Triceratops was not winning any races. But on top of that, we can just look at this animal from a dorsal view. Here, you can see the eyes. Let's draw a line through those to see what its field of view was like. This is a giant blind spot. It could not see if anything was approaching from this angle. It couldn't see it. But it's not all doom and gloom for Triceratops. We don't have to feel bad for Triceratops. It wasn't a victim. Because we see that some of our prior work showed that Triceratops was very, very good at turning. For example, we found that a roughly 8,000 kilogram Triceratops could turn 40% faster than a 6,600 kilogram T-Rex. So despite being nearly a ton and a half heavier, it was still able to turn considerably faster. On top of that, it also had a nearly spherical kind of ball and socket joint connecting its head to its neck, which meant it had a large amount of motion potentially possible. So let's look at the potential interpretations. Flight would have ended something like this. It's exposing its blind spot to its predator, and it's not running fast enough to get away. And it's exposing all of those vulnerable regions of its body where it could be torn apart. Fighting was its best option. It actually stood a considerably good chance. It doesn't even need to necessarily fight. It just needs to show, hey, these are large horns. These can cause very severe injuries. I see you. I'm aware of you. You better back off if you know what's good for you. This works very well for a lot of modern animals. So, kind of summary of what we found. T-Rex was an adept runner, especially for its size, which aligns with a lot of prior research that we and others have done. We also found that, like some of our own prior research, these two large herbivores living alongside T-Rex utilized some very different predator avoidance and deterrence strategies, flight versus fight. Such dynamics are very common in modern ecosystems. As they say, the more things change, the more they stay the same. Look at, for example, Cape and water buffalo in South Africa versus, say, zebra or gazelle or things like that, where Cape buffalo generally are going to potentially face a threat because those horns alone are enough of a deterrent in the majority of cases that the actual hunt or conflict never even occurs. But we still have more to go. We're going to be including far more dinosaur species. This is just the result of what has been finished right now. We're also going to be including T-Rex of different ages and sizes because we know that T-Rex changed considerably, though not as much as we previously might have thought, as it grew. And we're going to actually be running simulations. We're going to be putting these things into simulation software to actually figure out the optimal gait for these animals and optimize for how fast these things could go numerically. How fast could they get to that top speed numerically? How fast and how tight could they make a turn? And so we've got a lot of really interesting stuff, a lot of really cool insights into some of the ecological dynamics between some of these animals. And we still have a lot more cool stuff on the horizon. But thank you for listening. If there are any questions, I'm more than willing to take them now.
Cohort's been asked to provide some of this data for the movies that maybe dinosaur movie comes. They want. Have they asked you for was this one faster than that one or anything like?
I recently got contacted by the people who recently made the Netflix documentary, though I haven't heard back from them after my first response, so they may still be working on that. But a lot of the time for stuff like that, either they have kind of their own kind of on-site team, and especially if it's not meant to be a documentary, they're just going with whatever looks the coolest or whatever, whether or not it's realistic. Most of the time, it's done. Yes.
And how realistic is the Jurassic Park?
Not really accurate at all. Funnily enough, they actually tried filming that iconic chase scene with the Tyrannosaurus Rex moving at 35 miles per hour, only to realize that it didn't look real, because it looked like, in order to get the T-Rex to move that fast, they had to give it ludicrously long strides and incredibly fast stride frequency, to the point where it looked like that animal was weightless. So what they did is they filmed at speed of around 11 miles per hour, and then they sped up the footage post. And it turns out that that's a little bit slow for a T-Rex, but it's much closer than 35 miles per hour.
Here. What's weird, like, what is kind of the biggest uncertainty as far as is it just the overall fossil record and the lack of maybe the total variability in size of some of these dinosaurs, or what is your perspective? What is the uncertainty they're trying to overcome?
I would say some of it is in the kind of the exact sizes of certain muscles, and conflicting hypotheses about where those muscles actually originate or insert. And so what we try to do is, we kind of, like, for size, we generally try to go with something that is kind of an average, because it's actually very simple if we think, oh, hey, this animal was, much heavier, or it was a bit bigger. We can simply change those numbers and plug them into the same thing, and we'll get another answer. But we can predict, as long as we can predict how those changes would affect the results, we're in a much better place. It's more if we don't understand how those things are influencing the results that we run into issues. So, for example, we know what caudal was doing. We know the muscle's function. We can predict, oh, if it was a lot larger than we initially thought, because we know what it's doing and how it's contributing, we can predict kind of what the difference would be if it was much bigger or smaller. And so I would say kind of bigger uncertainties are, like, one of the reasons that we don't include certain taxa is there's just not enough skeletal data to reasonably really reconstruct that animal with any degree of certainty, to the point where it's not even worth it. So that's why the smaller dinosaur taxa, things basically below 50 kilograms, just are not in our sample. There's just not enough there. But overall, especially with the dinosaurs that we're working on, because they've been worked on and kind of been in our kind of record for over 100 years, we're in a much better place, and that's part of why we've chosen the ecosystem that we have.
Have you found any soft tissue at all, frozen, kind of to know muscle?
We don't really get, because that would be permafrost. That's much more recent. That would be things from, like, the Pleistocene, so the Ice Age. What we do get occasionally are kind of mummies, and that's usually a preservation of either impressions or of actual mineralized skin. And sometimes we will actually get some level of almost silhouette of the body, which can give us a lot of information. But also, one of the big things we can use is the bone, like the bone itself. For example, caudal has a very, very, very prominent insertion site on the femur, this giant ridge in something like Triceratops or Edmontosaurus or T-Rex called the fourth trochanter. And you can actually look, and there will be texture from where that tendon was pulling on that bone. And it's to the point where you can actually look for muscle and tendon insertions by, say, doing a CT scan of a bone, or doing even just a slice through a bone at an area where you think a muscle or tendon inserts, and you will actually see certain orientations of the actual fibers of that bone that reflect that muscle acting upon that region. That's how, for example, we further confirmed the extensive series of stabilizing and strengthening ligaments in the ankle of Tyrannosaurus rex. So many areas of really chaotic bone organization that are indicative of multiple tendons kind of holding something steady and therefore kind of pulling it in multiple different directions.
Many years ago, there were efforts to estimate energy budgets, how many calories were consumed by these large creatures. I would think that your work would really make or add focus to these estimates and how many calories needed to, if you're going to be running this fast or turning this quick.
Yeah, part of the problem is that it's really hard to estimate metabolic rate in that sense. We can get ideas of like, in terms of like, okay, how much oxygen would this animal be needing to kind of consume, but turning it into kind of caloric demands is a lot more difficult. But it is definitely something that I would love to see, like if we can figure something like that out, if there's any way we can actually get like a range of quantitative estimates that we can show are both based on data that we can obtain from the fossil record, and we can kind of use extant animals to ground truth, because that's the biggest thing we need to be able to do is we need to say, oh, this range of, we can't be like, oh, this tissue says that it's got this metabolic rate, and then not ground truth that, because where the heck is that kind of idea of making that inference coming from if you're not able to have something modern where you can measure its metabolic rate and then look and see, oh, do the bones reflect this? And then there's also the fact that you have to kind of sample across a large degree of generally both related and unrelated taxa to make sure that it's, for example, you're not biasing yourself if you say only use mammals or only use, reptiles or only use birds. You have to kind of make sure that your rule is widely applicable.
For conclusion that the Triceratops probably hasn't evolved stand by was that influence how you think they behaved as juveniles or adolescents? They're smaller, probably more nimble, but did they need the protection of a parent or
I don't necessarily think they needed it, but they're right now. The unfortunate thing is that we do not have a lot of post crania from Triceratops any younger than kind of the subadults. Basically, if it's Triceratops and it's less than 1,000 kilograms, we might have one or two bones from the non-skull region. And funnily enough, our segmental mass properties give us an idea of why that is. For example, basically the skull in adult Triceratops is about 30% of the entire skeletal mass of the animal, whereas the soft tissues associated with the head are, I think, less than, it's definitely less than 10%, but I think it's even smaller than that. So when animals are picking apart a carcass, they're obviously going for areas that have the most easily kind of caloric kind of intake. But with Triceratops, you have basically everything behind the head, and then the head doesn't really have a lot of meat on it. Something like T-Rex doesn't have a problem with that because it can just crunch through the bone and get all of that marrow. But anything else is generally not gonna be able to do that. And even if a T-Rex is going after that, it's still going to go after everything else first. So the skull is going to be what is left for last, and thus more likely to get buried. But Triceratops was probably a bit faster, but still, given that all of the other predators, as they got smaller, or rather, when they were younger, they would be even faster than they are as adults. I don't think that, unless Triceratops had just the most ludicrous kind of hind limb proportion changes of almost any animal, it was not ever going to be much of a runner. So I predict possibly, in addition to potentially living in kind of small family groups, at least until they got to enough of a size where they actually had more than just little nubs. I think it may have been a combination of camouflage and kind of sticking in groups.
How about that? Like it's preserved in the fossil record is related to where their flesh is. That makes total sense.
Yeah.
We got a personal question. How many reptiles do you own?
Currently, I think it's 14,
Figured you would have.
something like that. Yeah, I'd have to, let's see, 2 Nile monitors, 2 blue tongue skinks. That's 4 plus 5 snakes. Then we've got 3 tortoises. So that's 12. Then, yeah, 14. So, because, yeah, panther, chameleon, and then, or 13 reptiles and 14 animals total.
It's probably pretty obvious that a lot of them would be able to camouflage and hide or show their turtle first, you know. There's, you would think that, but it really would be different than today, maybe that they'd have a different color and different.
Oh, certainly. Yeah. We can't, predict, for most dinosaurs, we can't really predict their color. But we can get an idea of how much an animal would have to rely on camouflage based on relative locomotor performance. For example, if an animal is reasonably able to run upon spotting a predator, then camouflage isn't going to be quite as important as if that animal gets spotted, it's not going to be able to get away whatsoever. So, for example, things like certain geckos, like the famous leaf-tailed geckos, where when they kind of get onto the trunk of a tree, they're almost impossible to spot to the point where even their eyes are camouflaged. That's because while they can kind of scurry about relatively quickly, the things that eat them, if they get spotted, it's lights out. Whereas something like a gazelle or a wildebeest or something like that, like obviously avoiding being spotted is helpful. But if they are spotted, they still have a reasonable chance of escaping just through flight. And then for some of these animals, it's flight as well. But it's usually a combination of multiple things, and that's just kind of how biology is. There's never really a single simple answer.